Yeah. Welcome you all to the session on Introduction to VLSI Design Flow. So in this particular session, we'll be discussing about the important aspects of how a digital VLSI flow is established. So we'll start off with the motivation of learning this particular flow. So if you look at this slide, you can see that the application of VLSI products are profound. It finds utility across different domains, whether it be military or industry grade products to things like consumer market, including automotive test and measurement equipments, biomedical equipments, computers and storage, high-end servers, communication, broadcasting, security and energy management, office automation to industry 4.0 automation. You can find FPGA or ASIC products spanning across. So that means this particular know-how or knowledge about VLSI design and productizing using VLSI platforms find a variety of applications irrespective of your engineering stream. Also, if you look at the position of our country among the leading chip makers, you can see that India is a newbie. The 47% of market share is handled right now by the United States of America. The source of this particular infographic is a study by Semiconductor Industry Association, which was conducted in 2020. You can see that after United States of America, 20% of the market share is held by a small country called South Korea, followed by European Union, Taiwan, Japan, China, and so on. While India being such a big country and there is a huge demand for products involving VLSI in India, we don't find much of products coming out of India because of the sheer lack of infrastructure coupled by the low speed in coping up with the vast changing technology know-how. So if you look at the government initiatives, you can find that Government of India has recognized the importance of both capacity development in VLSI as well as infrastructure development. What you see in the slide is the cabinet decision of 15th December 2021, where a total of 2.3 lakh crore of incentives are being pumped to position India as a global hub of electronic productization. Also, 76,000 crores approved for development of semiconductor and display manufacturing ecosystem, that including establishment of fabs. The aim is to set up India semiconductor mission to drive this sector. So India semiconductor mission is approved to implement the policy roadmap for development of semiconductor products in India. Also, by this, the government is aiming to touch an export share of 5.15 lakh crore over the next 20 years, with a production target of roughly around 9.5 lakh crore over the next 20 years. And the whole aim is to be part of the USD 5 trillion GDP by 2025-2026. So why this particular information is shared is to motivate you, to impress upon you that there is a huge scope of learning VLSI, whether you want to work for a big product house to be positioned in India, or to be part of the design ecosystem worldwide. Now, if you look at how digital logic implementations are done, it can be classified into three major sectors. The first one is called a full custom ASIC. Here, ASIC basically stands for application specific integrated circuits. So if you look at the ASICs, there are three primary categories. One is called a full custom ASIC. The second category is called a semi-custom ASIC. And the third category are basically formed by programmable integrated circuits, namely programmable logic devices or PLDs, as well as field programmable gate arrays or FPGAs. Okay, so again the semi-custom ASICs are classified as gate arrays as well as cell based. The gate array based semi-custom ASICs can be further classified as channeled gate arrays as well as channel-less gate arrays. Similarly, the cell-based semi-custom ASICs are further classified into standard cell ASICs as well as macro cell ASICs. So we will see what all these means and how they are different from each other before we start with the VLSI design flow. First, let us look at what a full custom design is. A full custom design or a full custom ASICs, if you look at it, all the logic cells, okay, including the circuits, the layouts, etc., are designed specifically to target a particular technology node or a particular performance, and everything is built from the scratch. Okay, so this particular technology or full custom design is very complicated, and it is chosen if and only if the existing libraries or macros are not enough, okay, or the logic cells are not enough to meet a particular power consumption. Okay, if the power consumptions of the already available commercial off-the-shelf libraries are very high, to meet the target power, which should be a low power in our particular product, we design everything from the scratch, including the circuits, the layouts, the logic cells, etc., etc. This particular way of designing an ASIC, application specific integrated circuit, is called a full custom design. So the advantage here is it would be able to target any particular performance, and it delivers the highest performance at the smallest possible die size and perhaps at the smallest possible power consumption. So it is just like, customizing your product. Okay, it can be for a mission critical application, maybe some electronics which is going to be part of a satellite system. It has to be it needs to be remaining unpowered or minimally powered for a very long frame of time, and it need to obviously consume very less power, and of course it requires a certain amount of miniaturization. So the aim of this kind of circuit is to do a PAP optimization, that is to reduce the power, to reduce the area, and to improve the performance, or rather the frequency of operation. So in that case we will go for full custom ASIC design. And the disadvantage here, of course, the higher performance comes at a cost. The higher performance and the smaller size, okay, it will require an increased design time and obviously an increased time to market, and the design would be overall complex, resulting in an increase in the overall cost of the IC itself. Okay, so example of these kind of full custom designs, the classical examples could be most of the microprocessors, high performance memories, analog processors, then analog digital communication devices, sensors, transducers, voltage ICs for electromotive applications, automobile applications, and so on. Okay, the other category of ASIC could be semi-custom design, and as we have seen here, semi-custom designs could be gate array based or it could be cell based. So if you look at gate arrays, in gate array ASICs, what happens is the P and the N type transistors are predefined on a silicon wafer SRAs. As you can see in the bottom side, you can see two structures. The left side structure is called a channeled array, and the right side structure is called a channel-less array. Okay, the left side structure, you can see some channels in between the logic placements, which is missing in the right side channel-less arrays. So both of these structures form semi-custom design known by the name gate arrays. So based on the design from the customer, or the requirements from the customer rather, the interconnections are obtained from the design. The silicon vendor provides these on the wafers. Okay, the gate arrays can be again classified into two types, as I already told. The left side is the channeled array and the right side is channel-less array. Both represent gate arrays in general, But in channeled gate arrays, the interconnections between the logic cells are performed within the predefined channel. You can see that there are some predefined channels in between the logic cells. The interconnections are done there in the case of a channeled array. In the case of channel-less array or a channel-less gate arrays, the connections are made on one more upper metal layer on top of the logic cell. So this forms one layer. On top of that, there can be an upper metal layer which basically is responsible for establishing connections between the logic cells in the case of a channel-less array. So that's the difference between these two types of gate arrays in semiconductor design. Now if you look at the next type of semiconductor custom design, that's called cell-based design. You can see the picture on the bottom side of the slide. You can see that in the case of cell-based, some standard cell area is there, as well as full custom block area will be there. Okay, so a standard cell-based ASICs also uses a predefined logic cell like gates, multiplexers, flip-flops, adders, etc. These logic cells which are predefined or pre-designed are called standard cells. Okay, and these standard cells which are pre-designed are stored in the library of the CAD tool, and this library is basically imported into the CAD tool and the design can be performed. So these libraries will be made available by the fab and that will be imported to the CAD tool in which the ASIC is designed, and the design can be performed using the components from these libraries as inputs. Okay, so typically standard cell library designs are organized as rows, as you can find in the picture. The standard cell means the height are typically constant, just like when you are building a house, you will be having rows of bricks. All these bricks will be having standard sizes so that it looks very neat, and the delay will be minimal in the case of a chip, or the motor would be minimal in the case of a house building. When compared with logic level components, the standard cell designs can be implementing very complex functions like multipliers, memory elements, and so on. Okay. It can also contain larger and more complex pre-designed cells like microcontrollers and microprocessors, and these are often called as mega cells. So there will be mega cells and micro cells. Mega cells are nothing but larger and more complex pre-designed cells, whereas standard cells are not that complex but predefined cells which are basically imported to the CAD tool. They are made available by the fab and imported to the CAD tool for performing semi-custom cell-based design. So if you quickly try to compare these two designs, they differ not only in the way it used but in the case of performance also. The full custom, for example, in the case of full custom, as I already told, the complete design, layout, geometry, orientation, and the placement of the transistor, the whole stuff is done by the design engineer. Okay, whereas in the case of semi-custom, the commonly used design, layout, geometry, placement of transistors are inferred from the standard cell array, and the interconnections are given based on demand. So full custom design, the entire design is made without use of any standard library. You are basically creating everything from the scratch, I told, and that forms your library element. Whereas in the case of semi-custom, the design is completed with the use of multiple library. Okay. So obviously, development time, the design cycle, the time taken for the design process to mature will be very high in the case of full custom, whereas it is relatively lesser. The maturity time period of the design would be relatively lesser in the case of semi-custom. Similarly, the full custom gives you a full spectrum of opportunities for performance improvement, whether it be area or die size reduction, whether it be power consumption reduction, or whether it be performance improvement in terms of frequency of operations and so on. The full custom gives you the complete spectrum or scope of improvement, whereas it is limited in the case of semi-custom because you are dependent upon the net performance of all the standard cell libraries which we use. Similarly, full custom has very less dependence on the existing technology nodes, whereas there is a complete dependency because the macros or the standards and libraries which are made available are bound to work only on an existing technology. So full custom is a higher cost because it's everything from the scratch, higher design cycle, longer time to market, more labor, it's a higher cost. Whereas semi-custom, relatively lower cost compared to full custom. So this is a pictorial depiction of what we discussed so far. If you look at on the y-axis we have the circuit performance, and on the x-axis we have the design time. If you look at it, require more time, okay, for full custom design to mature, whereas it is relatively lesser in the case of semi-custom design, which is shown by the blue line. Okay. On the other hand, if you look at the circuit performance, the semi-custom design gives you lesser scope of performance improvement in terms of PAP optimization, whereas it would be having more scope of improvement of performance in the case of full custom. Now with this background, let us move on to the basic ASIC design flow. So what you see on the screen is the ASIC design flow, which is kind of generalized, but from design house to house there could be minor variations in individual steps. So if you look at the ASIC design flow, you can classify this ASIC design flow into two areas. Basically it's called as a front end as well as a back end design. So in the front end part, everything starts with a customer requirement. So if you're a product company, the people like techno managers who understand technology as well as the consumer needs as well as the business point of view are made responsible to collect the customer requirement. The customer requirement would be very, very naive. It may not be in terms of technical terminologies. They will tell you how much size their product should be, how much power it should be consuming, or how much should be the standby time of their product, and so on. So the responsibility of the techno managerial team is to convert this customer requirement or the requirement analyzed into something called specification, which are nothing but technical jargons or technical terminologies which are used to represent the performance as well as the modalities of the circuit, and these specifications will be converted to by another team of experienced designers, often called as architects. They are responsible for building an appropriate architecture of the design. Okay, we might be familiar with the architecture of many processors, DSPs, and so on. So basically, an architecture is it's a representative view of how the design should look like, whether it be an ASIC or a system on chip. So this architecture will be broken down into different logical portions. Okay, for example, the architecture of a microcontroller may be carrying something like an memories, something like arithmetic and logic units, something like registers, something like a lot of control units, data path units like adders, multipliers, and so on. So this logical breaking is given to another team of RTL design engineers. So RTL design engineers are those people who are capable of doing the design entry, okay, to a electronic design automation tool. So they can represent this architecture in terms of a schematic diagram, or they can go for a block diagram kind of design entry, or they can go for a RTL design. So RTL designs are basically descriptions of your circuit or the descriptions of your hardware written in hardware description languages like VHDL or Verilog HDL or System C or say System Verilog and so on. So RTL here stands for Register Transfer Level. It is a way of describing a hardware so that it can be converted to a real circuit structure. Okay, so once RTL design is done, it is pushed, it is subjected to a variety of functional simulations wherein the design engineer himself or herself will be looking for possible bugs or compilation errors, and those kind of stuffs will be resolved at that stages. And once the design engineer is satisfied about the conformity of the design or the description to the specification, he will be pushing it to another team called RTL verification engineers. So RTL verification engineers are basically those people who have capability to write test benches or create verification plan and subject the RTL design, okay, to a variety of test cases. Okay, there are a variety of methods employed for that, and languages like Verilog, and more prominently something like system Verilog is used here for verification purpose. So verification is essentially checking the conformance of the design to the specification independent of the designers. Okay, so the designers have already understood the specification and have designed something, but they might be missing certain corner cases, certain examples of inputs, upon application of which the design may malfunction. So the work of RTL verification engineer is to debug the design at a much more exhaustive level that is not possible at the design level. Okay, so after RTL design verification is done, it is subjected to something called a synthesis. So synthesis is basically a process of converting your design into structural equivalent. So these two steps, which is called as the design entry or design RTL design, as well as RTL verification, along with some portion of synthesis, possibly you can call it as a front end design, because the front end itself, people will often verify the design on some prototyping platform like FPGA before we take it with the backend design for the ASIC flow. So design entry is basically, as I told, representing the design in terms of or with the help of hardware description languages, and RTL verification is all about finding answer to the question that if the proposed design will do what is intended as per the customer or not. Okay, so RTL verification becomes a complex task out of the sheer volume of test vectors or test cases that the verification engineer has to apply on the design so as to verify that design as exhaustive as possible. So if you look at it, in the verification task, almost 36% of the total verification cycle is consumed by the debug process. Test planning take a large amount of time. This is about the not verification cycle, the total design cycle. So so many times the design will be back annotated between the verification engineer and the design engineer, and 36% of the time will be spent upon roughly on the debug itself. Okay, so other tasks of the verification engineer include planning the test cases, developing a test bench, creating and running the test using the processes of regressions and stuff like that, and documentations and so on. So RTL verification altogether is a very complex task, and it's a major time consuming task. So if you assume the total front end cycle to takes 100 days, almost 70 days will be consumed, or 70% of the time will be consumed for verification, and 30% of time, roughly 30 to 40%, will be spent upon the design process. If you look at the back end of the flow, there are a lot of steps you can see here, including synthesis, DFT, which stands for design for testability insertion, floor planning, followed by placement, and CTS here stands for clock tree synthesis. It is followed by another step called routing, then design sign off or design verification, then fabrication, packaging and testing. At this stage you can before this stage you can have something like a DFM or design for manufacturability, and once everything is foolproof, the packaged and the device is tested foolproof, it will be given for chip tape out, and you will get the chip as we can see in our normal days. What we get out of this is a die which will be packaged to give it rigidity as well as to give it a physical structure that can be handled by the consumers. Okay, so that is how an ASIC flow is designed. We will look at what is meant by synthesis, floor planning, CTS, routing, and so on, which forms the backend stuff now. So backend design steps, if you look at, the first step could be logic synthesis. So the process of logic synthesis, your verified RTL, okay, it is actually converted to a structural equivalent, or it is converted to a something called a gate level netlist, okay. And this gate level netlist is very subjective. It is subjective to the target technology of the chip. Okay, you have a particular RTL design, and we synthesize it for a 90 nanometer technology. The resulting file will be substantially different if we try to synthesize it for a 45 nanometer technology. It will be substantially different if you are trying to create a netlist for a field programmable gate array or some other programmable logic. So logic synthesis is a step which takes the design file RTL as one of its input. It also takes user constraint file, which are the user given constraints of the design. Also it takes a lot of library inputs. So the output of logic synthesis is a combination of all these three inputs. So during logic synthesis, you can also do something called a DFT insertion. As I already told, DFT here stands for design for testability. In this stage, the techniques are applied which facilitate a design to become more testable after production. Okay, so what happens in this step is, you have a particular design. So alongside that design, certain extra logic is inserted for production, okay, so that post production testing of the design logic will become easier. So it is giving certain amount of controllability and observability to your design. So DFT, the purpose of DFT is to insert certain additional logic into the design so as to make the testing of the chip easier post production process. Okay, so after DFT insertion is done, typically the next step is floor planning. And floor planning is a process which is an iterative process which basically does few things. It determines the macro placement, the power grid generation, and IO placement. So the macro placement means the logical placement where things should be placed on your die. Okay, it's just like we are we are building a house. We need to basically first decide where should be the bedroom, where should be the dining room, where should be the family living room, where should be the kitchen, and so on. So that arrangement, also we have to plan where should be the power coming up, where should be the exit and entry, and so on. So IO placement, power grid generation, macro placement, everything happen. It's not actual placement, it's about determining where it should be placed. So those steps happen in the floor planning stage. So floor planning basically identifies where the blocks macros should be placed on the chip. It also determines the routing areas between them, or where the connection should go in between them. It determines the size of the die and creates wire tracks for placements of standard cells. It determines the input-output pin pad placement information as well. So these are the functions floor planning should do. And further, the next step should be the placement. In placement step, the gates in the netlists are assigned non-overlapping locations on the die area. So placement is the actual place where we decide how we bed, with the house example, how what should go in a particular room and so on. So logic placement is a very iterative process in which in each iteration certain refinement is achieved. Okay, so that the performance and power performance can be improved given the power constraints. The next step in our design after placement is clock tree synthesis. Clock tree synthesis is a stage in which a particular clock tree is built with the help of inverters and buffers. The purpose of building a clock tree is to balance issues like clock skew as well as minimizing insertion delays in order to meet timing and power requirements or constraints. So clock tree synthesis basically ensures that a structure with the help of buffers and inverters are formed so that every element in your SoC or ASIC get clocks with minimal delay and without much of skew problems. Okay. The next step is routing, which is there is a local routing as well as a global routing. Basically, routing is about establishing wires and interconnects between the gates. Okay, when the netlists are added. Similarly, the very next stage is physical verification and sign off. So in this, many things like conformity to rules are done. For example, there are a variety of rules like design rule check or DRCs, electrical rule checks or ERCs, layout versus schematics, and so on. So many checks are there, which are basically subject to a technology node as well. So these, in this step called physical verification and sign off, it checks whether the design meets timing performance, that is there is no setup time violation, no hold time violations, and so on. Similarly, there is no noise issues, and it has sufficient signal integrity, and it can give a proper yield. Okay. There are no such violations in respect to timing, signal integrity, or DFM. So these things are taken care of in the physical verification and sign off step. Sometimes there could be a step called design for manufacturability shown separately in the flow. So in this step, basically the design is modified to the to the extent possible to make it easy and efficient to be produced. Okay, so basically in this step the DFM is achieved by adding extra wires, adding dummy layers, etc., all complying to the design rules set by the foundry. Now after this particular physical verification and sign off step is done, which includes design for manufacturability steps as well, the design is the chip, the die is taken for packaging and testing. And in this step, basically it is ensuring that there is no logical faults available in the chip, and the packaging is done following the manufacturing rules. So often you hear about one more step called post silicon validation, which basically involves operating one or more manufactured pieces of chips in the actual environment so as to validate the correct behavior over a specified operating conditions. So once post silicon validation is also done, the chip is ready for mass production. That process is called chip tape out, where the design data is turned into photo mask in mask data preparation. Now, so far we have seen the ASIC design flow and the difference between full custom and semi-custom ASICs, including the subcategories of gate arrays and cell-based structures of semi-custom ASIC. Now, once we look at the third category of ASIC, which are basically programmable ICs, there are many subclasses in that. One is called programmable logic devices. There are multiple categories like simple programmable logic devices or SPLDs. There are complex programmable logic devices or CPLDs, and also there are slightly more complex programmable ICs called field programmable gate arrays or FPGAs. So if you look at what is the major difference between a very much frozen ASIC versus a reconfigurable FPGA. FPGA is, as I told, it's a reconfigurable or programmable IC only. If you look at it, ASICs once formed cannot be reconfigured with a different design. Okay, they contain only one design in them for the whole of its lifespan. Whereas FPGA is for reconfigurable computing. It's a platform, or it's a fabric that can accommodate multiple logic. So you take an FPGA, you put a design. Once that design has served its purpose, you can use the same platform by reprogramming it for a different design. So that is the benefit of FPGA. So ASICs are basically, the time to market is very fast in the case of FPGA. Okay, because the design flow is quite simple, whereas the time to market in the case of ASIC is relatively higher, and the design flow is more complicated because it is more optimized for performance compared to FPGA. So for the set reason, ASIC is basically intended for bulk production, whereas FPGA are not really suitable for bulk production, because the cost of the unit cost of an FPGA is quite high compared to that of a ASIC, which goes for mass production. Okay, and if you compare the performance, the FPGAs can give only from very basic to medium level of performance. Though the FPGA vendors call it high performance FPGA, that basically means it's high compared to its previous version. That's it. It's never comparable to an actual ASIC, which is custom made, full custom ASIC. So performance on FPGA are medium. It can give you limited operating frequency on a particular target node, whereas ASIC has higher performance. It can give you higher frequency with the same technology node. Okay. Similarly, if you look at the unit size of FPGA are medium to high, whereas it's very low in the case of ASIC. So does the power consumption. It's very low for ASIC, very high for FPGA compared to ASIC. So FPGAs are basically tools to prototype, to emulate, to prototype, and to validate a proof of concept. Of course, FPGAs form part of many products now, but as the product matures, there would be a need for miniaturization, there would be a need to reduce the power, there would be a need to make the product deliver a higher performance. Then the ASIC is the only answer for that case. So, but an ASIC being a very costly product, it is built only after validating the design for permanent use. It's prototyped typically on FPGA, and the design is made to mature, and only then once it is foolproof, it's taken for an ASIC tape out. If you look at the types of ASIC which we discussed here, gate array, cell based, and FPGAs, you can see that the standard cell ASICs has the highest performance compared to a gate array as well as an FPGA. The time from design ready to the first part is almost zero in the FPGA. That is its major advantage, whereas this is very high in the case of a standard cell ASIC. Whereas standard cell ASIC comes with a high benefit of having lowest high volume cost. Okay. So the negative of standard cell ASIC is that it takes long time to first product, and the time to market is the negative of standard cell ASIC. Whereas the negative of FPGA is low performance. The gate arrays also carries a performance slightly better than FPGA, but not sufficiently as good as a standard cell ASIC. Okay, so basically gate arrays are used for FPGA shrink. Okay, when you have a foolproof design on an FPGA, you want to shrink it to be ready for an ASIC, you put it on a gate array. Now let's try to understand what an FPGA is. This is an intuitive view of FPGA. This is not what an FPGA is. Okay, but for those people who are totally new, they can imagine it as a it's a breadboard kind of stuff, where you are given with most of the macros. For example, if you take a digital circuit, you may require a lot of combinational macros or units like multiplexers, adders, lookup tables. You may require certain memory elements like ROM, RAM, etc. You may require certain gates array which can be configured, okay, to represent different logic. You may also require certain flip-flops, counters, etc. to build sequential circuits. So FPGA can be imagined. This is not FPGA as a tool, but it can be imagined intuitively as a reconfigurable platform wherein all these elements can be made to be incorporated in the design as intellectual property codes, and connections can be established in a reconfigurable manner. So these built-in components, you often call it as a macro, and the wiring part, the synthesis part, or the building part is done with the help of certain electronic design automation tool. Most of these tools are called as a synthesis tool, while it takes the RTL as an input and convert it into the equivalent structure. So inside an FPGA, mostly FPGA carries 3 building block. It has these boxes called logic block, which basically consist of reconfigurable logic. So depending upon what design you are putting in, your design may be consuming multiple logic blocks. The design will be partitioned, and each logical block will be put on a logic block, which is shown there, which is often called as configurable logic block in the FPGA terminologies. Similarly, it has something called what you can see around this box. The outer box are pins which are reconfigurable. So it is called as configurable IO blocks that can be configured to be working as input pin, output pin, in-out pin, or bidirectional pin, and so on. Similarly, you see in between these white boxes a lot of wires, which are actually a array of interconnections which can be programmed so that the routing can be reconfigured. So if you look at how FPGAs are, FPGA based design is done, this is the normal flow of it. What you see on the left side is more like a generalized flow, and what you see on the right side is the flow which is given by an major FPGA vendor called Xilinx. So if you look at on the left side, you can see in a nutshell the first part of FPGA design flow starts with design entry, where the design is entered as a netlist. And the design is entered as a schematic, or mostly in terms of a hardware description language. So this design is subjected to verification called behavioral simulations, and of course it is then subjected to the process called design synthesis. So after design synthesis, you will get certain file formats which is again subjected to behavioral simulations. So once the synthesis is proven to be correct, it is given to the next step called implementation. So implementation produces a lot of sub-steps, or involves a lot of sub-steps like design translation, design mapping, design place and route. Then comes a step called bit stream generation. Okay, so Xilinx call it bit stream. It comes with a extension of a dot bit, and that is used for basically it is dumped into the memory, it is dumped into an FPGA so that the FPGA get reconfigured according to stream. So the bit stream file is basically a text file like lookalike, which carries ones and zeros, but these ones and zeros, once it get dumped onto the FPGA, it will reconfigure the FPGA so as your design is implemented. Okay, so the synthesis produces a particular file format. Normally in Xilinx terminologies, it is called a native generated circuit file or NGC file, which is again subjected to a lot of logic or timing simulations. At each step of implementation, typically, each step of implementation, like translate, map, place and route, some kind of simulations are running so as the design is verified. Okay, for example, something like functional simulations are done, layout versus schematic things are done, then static timing analysis is done. If there is any timing violations, it will get back annotated to the design implementation stage, where it will get corrected by the designer. So once everything is foolproof, the bit stream is generated and it is dumped onto the FPGA for in-circuit verification or emulation. So that is FPGA design flow. Now if you look at the FPGA market share in 2020, this is statistics by Global Market Insights. In 2020, the FPGA market is worth 6 billion. By 2027, it is supposed to rise to more than 15 billion, with Asia Pacific compounded annual growth rate of 16%, whereas compared to the American counterpart. So if you look at the CAGR or growth rate, if you look at the growth rate also, the normal SRAM architecture as well as those FPGAs having less than 28 nanometer segment is going to grow the peak. So learning FPGAs are also worthwhile while we are trying to get into the VLSI design domain. And this is another important information that the major FPGA vendors, most of the companies originally they were known as Xilinx, Altera and so on. Now Xilinx is acquired in 21 by AMD, And the next bigger company is Altera, and Altera is now part of Intel. So you go to these two websites, that Xilinx as well as Intel, along with other vendors like Actel, Lattice Semiconductors, Cypress Semiconductors, and so on. You will find plenty of resources related to FPGA, its design flow, its design resources, and so on. So in this session, what we have discussed is basically the need for learning VLSI, how big is the VLSI market and how big it's going to be. And we have seen what are the different digital logic implementations categories, like like full custom, semi-custom, programmable logic, and the subcategories, and how they are different from each other, and which one is having more advantage than the other in a given situation, and so on. We also have seen the typical ASIC design flow, and we have in detail seen all the design flow steps. Also, we have seen the major differences between ASIC and FPGA, when an ASIC is put to use and then when an FPGA come into picture, and so on. We have also seen the typical FPGA design flow and the FPGA market as well. With that note, we will conclude this session. Thank you.